Illumination source separation using a flash photography technique, re-implementation and evaluation in variety scenarios. Real-world lighting often consists of multiple illuminants with different spectra as shown in the input image. Separating and manipulating these illuminants in post-process can be used to support various applications like white balancing, light editing, and RGB photomatic stereo. In this project, we aim to implement and evaluate methods presented by Hui et al. To solve this problem. Let's assume that the scene is Lambertian and is imaged by a 3-channel color camera. Here, camera has camera spectral response Sk lambda, and the scene has reflectance spectra rho p lambda at pixel p, and illumination has light spectra of Lp lambda at pixel p. Then, the intensity of the image observed at a pixel p can be expressed as this. And when the scene is lit by n different light sources, the intensity can be expressed as this. To separate multiple illumination images, we need to estimate the reflectance, shading, and illumination parameters, as well as separating the image into n photographs, which is very hard in various problems. The parameters of interest are infinite dimensional, and the multilinear encoding of the reflectance, shading, and illumination parameters leads to a highly ambiguous solution space. To resolve these challenges, the authors make 2 key assumptions. The first assumption is that the reflectance and illumination spectra in the scene are well approximated by low-dimensional subspaces. With the setup bases Br lambda and Bl lambda, reflectance and light spectra could be expressed as weight sum of the bases. The each weight is called as reflectance coefficients and illumination coefficient. If we could predefine the basis for the reflectance and illumination, the intensity of the image could be expressed as this matrix multiplication. Now the unknowns for pixel intensity are reflectance coefficients, shading term, and illumination coefficients for each illumination. The second assumption is that we are available to have access to flash photography. By subtracting flash image from no flash image, we can compute pure flash image, which well embeds reflectance information. With these assumptions, we could perform illumination separation in following steps. Firstly, we solve for reflectance coefficients. When we look at the pixel intensity in pure flash image, we have AP and shading term as unknowns. If we defined new term alpha p, we can solve for alpha p because we have 3 intensity measurements from each color channel and 3 unknowns. In second step, we can express pixel intensity of no flash image with alpha p from the first step. By defining beta as this, again we have 3 unknowns and 3 intensity measurements, same as the step 1. We are able to solve for beta as well. Normalizing beta p gives us gamma p that is invariant to reflectance. Now we can see that the term gamma p lies in the vector space with non-negative weights for the illumination coefficients, and the space is called conical. Now we can estimate each illumination coefficient for each light source by fitting the tightest conical for all pixels and identifying the corners of the conical. For jth light source, the estimated intensity is expressed as this equation in the original paper, and we found that the denominator absolute alpha p was missing. This oversight has been identified and corrected in the final report. This correction is crucial as it ensures the accurate normalization of the reflectance coefficients thereby improving the fidelity of the image separation process. Now going on to the results, first we evaluate the performance of the re-implemented methods on the open datasets with two illuminations. We intentionally selected the scenes that were not presented in the original paper. The author's methods successfully separated the image into two components, actually by a single light sources. Then, we also evaluated the performance of the methods on our own captured images. We intentionally selected the scenes that would violate the inversion assumptions of the original paper. Both scenes contain shiny objects, for example, laptop emitters here. As shown in the results, we could find that the proposed method failed to separate the image, resulting unpleasant artifacts. Please check the submitted report for more details and discussion. Thank you.